Okay, welcome back to EE210B. Let's continue our discussions on inference strategies over networks. So the material for this lecture is based on chapter 12 from the text that you have, which again you can download from our website. Now, if you remember what we did in the last few lectures, we spent several lectures on establishing that the networks are stable, right, in the mean sense, in the mean square error sense, and in the fourth moment error sense. And then I spent 2 lectures deriving performance expressions for these networks, right? We ended up with an expression for the mean square deviation, MSD, and for the excess risk, ER, for the network. And these expressions depended on several parameters. They depended on the Hessian matrices, they depended on the noise, gradient noise covariance matrices, and on the entries of the Perron eigenvector, right? Very good. So now we know how to study the performance of these different networks. So let's now look at these performance expressions and see what they tell us about the network, right? How do we compare networks to each other? If I give you 2 different topologies connecting a certain number of agents, which one would converge faster? Which one will give you better MSD? Or does it make a difference? Does the topology make a difference, right? Can I make networks match the performance of centralized solutions? Okay. How do I design the combination weights? How do I select the combination weights? Questions of that sort. That's what we are going to see today, okay, in this lecture. So here I'm reminding you, right? I'm reminding you of the definitions. So H sub K is the Hessian matrix at agent K at the Pareto solution, right? And G sub K is the gradient noise matrix, right? Remember that because we are dealing with the general complex case, we extend the gradient noise vector, right? SKE, where you put the SK and the SK star transpose, right? It's a 2m/1 vector. And this is the covariance matrix of it, the one below here in the complex case. And in the real case, it's just RS, right? Which is the expected value of SS star. Right? The RQ is the expected value of SS transpose, if you remember, right? So this is just to remind you of what these parameters are, okay? And this is the performance expression we derived last time, right? So here you have the MSD, and you have a similar expression for the excess risk. This is the MSD over a distributed network, whether you are using consensus or diffusion strategies. This is the performance to first order in mu, or mu max, where mu max is the maximum step size. It depends on G's, on H's, and on the Q's. And remember that the Q's are related to the P's, right? And to the step sizes, okay? And from this expression, you observe also that the performance is equalized across the agents. All of them will have this performance to first order in mu. Differences start appearing in second order factors, okay? But to first order in mu, all of them will look similar, and that's the expression, okay? And this is the performance of the network. If you average across the network, that's what you get, okay? Very good. And then I showed you an example last time. I said, let's consider a mean square error network where each agent has a quadratic cost. In this particular case, the Hessian matrix will be block diagonal, RU transpose. So I'm assuming uniform step sizes, uniform covariance matrices in this example. And the covariance matrix in this case for the gradient noise will have this form. I don't care about the off-diagonal elements because once you multiply H inverse by G and take the trace, the off-diagonal elements do not matter. Remember, I did this example last time. And then if your matrix happens to be doubly stochastic, then the Perron entries will be 1 over n. N is the number of nodes. And we derive this expression. Remember, I'm just reminding you of the example. This is the performance of your network. No matter how large your network is, the performance will be given by the average value of the noise power across the network divided by 1 over n, multiplied by mu m over 2. And that's exactly the expression we derived earlier in this class for the centralized solution. So for mean square error networks, the distributed solution can match the centralized solution. And in the next few slides, you are going to see that this conclusion actually is more general. It's not only applicable to quadratic costs, to more general costs. I will establish the same result for general costs, J sub k, right? That satisfies the usual conditions that we have, right? Convexity and so forth, okay? But another thing I mentioned last time is, even though the distributed solution can match the centralized solution, and therefore is better than the non-cooperative solution, right? If you have n agents running independently of each other, what would be the average performance of the non-cooperative solution? You would just have 1 over n, one of them, right? The other will not be there, correct? You already know that, right? Yes?
Yeah, now you say that the distributed case, the performance is the same as the centralized. And how about the rate? How about the...
Yeah, you asked the same question last time, and the rate of convergence is the same, right? You saw, I showed you the expressions, okay? So, so here you see that the distributed solution, right, will be better than the average solution over the non-cooperative network, right? But what about the individual agents? Each individual non-cooperative agent will perform according to mu m over 2 times the corresponding sigma v, right? Is it always true that this average that you get here, scaled further by 1 over n, is always better than each individual performance? We saw before that this is not the case. The same thing will hold here, right? So for example, okay, let's take an example here. I have 2 agents only. The noise power at one is sigma v squared. The noise power at the other is 5 sigma v squared. So the average will be 3. And then you further divide by n, that gives you 1.5, right? So the performance in the distributed network will be proportional to 1.5. The proportional, I mean, because you have the mu m over 2, right? The performance at node 1 will be proportional to sigma v squared, which is better. At node 2, it will be worse, right? So this is an example where, even though the network performs as well as the centralized solution, better than the average non-cooperative solution, you don't necessarily perform better than each individual agent. You understand it? The same problem we had before with this centralized solution, okay? So that's what I'm saying here, okay? It's not the case that every agent, therefore, will benefit from cooperation. The network as a whole benefits, but not every individual agent. The natural question becomes, like you asked last time, right? Can I pick the A to make sure that I don't only improve over the non-cooperative solution on average as a group, but individually as well, right? And we will see that the answer is yes, we can do that, okay? Very good. Okay. And that's exactly the question that I'm asking here. Can we do better? Okay. So I'm going to answer these questions in the general case, not just for quadratic costs, but for general costs, okay? Convex costs. So this is my setup. I'm going to assume the step sizes are uniform across the agents. Why? Because I'm comparing with the non-cooperative case. The performance for each non-cooperative agent is proportional to mu, right? So to normalize, for these comparisons to be meaningful, I don't want the performance to vary just because a node is using a different mu than another node, right? You understand? So let's assume all the nodes are using the same step size, and let's assume also all the nodes are interested in the same solution, right? So that you compare how well all of them are doing in meeting the same objective, right? So that the comparison is meaningful. Okay. Okay, so here it is. So I'm going to assume that all of them are interested in estimating the same omega 0. So let's assume they all have the same minimum, which happens, for example, in the quadratic case. They all have the same step size, and all costs are strongly convex, so that the non-cooperative agents are able to solve the problem and find the minimum. That's all, okay? Very good. So, but now this is not necessarily quadratic. Now, in the previous lectures, we derived these expressions. I'm just listing them for you here, okay? So let's look at them. Look at the second one. What was this? This is the performance of the non-cooperative agent K. If you have agent K running an algorithm, the stochastic gradient algorithm on its own, what performance will it get? Mu over 2. H is just the data type, complex or real, right? H is 1 or H is 2. So forget about H, okay? trace of the Hessian at agent K inverse times the gradient noise at agent K, right? Okay. By the way, this quantity here will come up many times. I'm going to be calling it theta K, and I'm going to put a square just to emphasize that it's a non-negative quantity. Okay, so I call it theta K squared. Fine, so this will be my notation moving forward. Now, the centralized solution, the performance was, I add the Hessian matrices across all costs, inverse times the sum of the G's, and down here you have the corresponding expression for the network. It's very similar. What's the main difference? The main difference is that they appear scaled by the Perron entries, okay? So here I'm assuming this is for the case of consensus or diffusion, right, where the QK is mu times P. Fine? So see the relation? And this is the average performance over the non-cooperative network. So what do I want to do now? Okay? I want to show the following things. These are the results we are going to show. First of all, if the network is, well, you can see it right here, right away, okay? I don't need to go through the proof. Let's assume that my network is using a doubly stochastic A. What will be P? 1 over n. If you put 1 over n here, 1 over n here, how does the first expression compare with the last expression? So it's obvious to see that. Even more generally, distributed solution matches the centralized solution, right? So that conclusion is still there. Okay. Now, in the doubly stochastic case, how does the distributed solution compare with the non-cooperative solution? How does the centralized solution compare with the non-cooperative solution? We proved this before. This was the lemma we proved earlier in an earlier lecture, right? Using some linear algebraic arguments, that this expression 1 here is always less than expression 3. We proved this analytically. Okay, if you go back, you will find this result, okay? And therefore, in the doubly stochastic case, since this becomes the same as 1, the same conclusion will hold here, right? So for doubly stochastic cases, networks, the network will perform as well as the centralized, better than the non-cooperative network, right? And what about on average? But what about at the individual level? Well, you already saw an example. Even in the quadratic case, that's not true, right? So you only need an example to show that this statement is not true, right? So here at the individual level, this is the expression, right? Because when you put 1 over n, at the individual level, it's not necessarily the case that this expression here will always be smaller than this expression. Correct? Okay, you only need one counterexample. I already showed you one for the quadratic case. Okay, of course, there are cases where this will be smaller. For example, let's take an example. Okay, let's take an example where the H's and the G's are uniform across the network. It so happens that H and, okay. So what will you get here? The sum of P is 1. You will get here H inverse. What will you get here? You will get, no, sorry, let's assume doubly stochastic again. Well, okay, I'm still talking about the doubly stochastic case, okay? Here you will get NG, right? That NG, the N cancels the N that you have here that came from the P's, right? So then the expression becomes the same.
It's N squared.
Sorry, there is N.
There's an N inside H.
So what you have here? Anyway, I have it in a future slide, so we can look at it more carefully here. Okay. Sorry, I already said all of this, okay? That's why I'm skipping it, okay? So I'm now focusing on the individual agent performance. When is this smaller than that, right? In general, it's not. I gave you examples, okay? And in some cases, right? For example, when this is uniform, what do you get here? You will get 1 over n H inverse. What do you get here? NG, correct? So this cancels that. And you have an additional 1 over n multiplying the trace H inverse G, right? So if the Hessian matrix is a G, and so there are cases where this holds even for a doubly stochastic network, right? But not in general. Fine? Okay. Very good. So that's what I'm talking about here, okay? So in that case, the relation will hold. Okay, so this is the example. I already explained it even before getting to the slides. Okay, so that's what happens here, okay? So this is the conclusion, that the performance of the network will match the centralized solution and will be better than the non-cooperative on average, but not individually unless some particular conditions hold, okay? So as a whole, as a group, you will always benefit from working together. This is what this is saying, right? The group will benefit from working together, and you can do as well as the centralized solution to first order in mu. Yes?
Shouldn't this be strictly less than?
Yes. Yeah, the lemma was strictly less, right? Yes. Okay. Fine? Okay. Okay, let's continue. Again, I'm just repeating it with more colors, okay? And I think there is a typo. Strictly speaking, it's not wrong, but that's the statement, okay? So I'm giving you an example. This is the metropolis rule. If you remember, if I'm an agent, K, here's my neighbor L. He has a degree, NL, I have a degree, NK. Degree is the number of neighbors you have, right? So the weight I'm going to assign is inversely proportional to the maximum of our degrees. This is called the metropolis rule, okay? Very popular rule. What's nice about it, it's doubly stochastic. You can verify. Columns add up to 1, rows add up to 1, okay? So the Perron entries are 1 over n, right? So if you want to simulate a network with a doubly stochastic A, you can use this, right? Okay. I have an example now. This is what I'm doing here. Okay, I'm running an example. This is the step size. Okay, real data, 20 agents. Okay. I'm running diffusion, adapt and combine, and I'm comparing with the centralized. I'm just running a simulation to illustrate these ideas, right? So let me go to the curves. There it is. You can see that the diffusion and the centralized are essentially on top of each other, and they match the theoretical expression, okay? Which is interesting to conclude that the network, imagine, this can be a very large network and it can be very sparse, right? Right? You can have, let's say, 10,000 agents, and each agent only has 2 or 3 neighbors, and yet the network is able, in steady state, right? Here, coming back to your question, the convergence rate, right? It cannot be clearer than this, right? Okay, and the steady state behavior. Okay, very good. So you get the point. Now, what if I move to left stochastic policies? Okay. Because in the previous result, I showed that on average, I will do as well, right? The network as a whole will do as well as the centralized solution, better than the average non-cooperative solution, but not necessarily better at the individual level, okay? Can I come up, okay? Can I choose my A such that I will always do better at the individual level as well, okay? That A has to be left stochastic. It cannot be doubly stochastic because there are counterexamples for doubly stochastic policies where this is not possible, right? Very good. So let me show you that indeed there is a left stochastic A that allows you to achieve that kind of behavior, okay? So I have to tell you what A it is, right? So to solve this problem, this is what I'm going to do, okay? I'm going to solve it in this case because for this case we have a closed form expression for the solution, okay? Not in the general case. So I'm going to solve it for the case where the Hessian matrix is uniform across the agents. For quadratic costs, this is very reasonable because this is usually the case. The RU is the same across the agents, okay? In machine learning, in pattern recognition applications, you have the different agents are interested in minimizing the same risk function, and the Hessian matrix ends up being the same. So this is not an uncommon situation, okay? Now, when the Hessian matrix is the same across the agents, okay, here I'm repeating the expressions, okay? The performance for the non-cooperative agent will be the trace of H inverse GK. G can still be different, okay? For the network, what will be the individual performance? Here you will end up having H inverse times sum of p's. Sum of p's is 1, right? So the sum of p disappears from here, and that H inverse I can put it here, correct? Okay? So the performance becomes the trace of the sum of p squared H inverse G. Here you have trace of H inverse G, correct? Okay. So now I would like to formulate the following optimization problem. This is my problem. This is the performance at a single every single agent, right? This sum. Okay. Of course, I remove the scaling factor. It doesn't matter, right? Okay. So now I'm asking myself this question. I'm given the topology. I would like to pick an A. I would like to pick what coefficients, weights to put on the edges, right? So I would like to pick an A such that those P's that appear here are the Perron entries of the A, right? And I would like to pick the A that minimizes that cost. At least find one such A, okay? You can find others in your homework problems, okay? Let me find an A that solves this problem, okay? You understand what I'm saying? Very good, okay? You see, I can switch, just so that I can bring the trace inside. Take the sum outside, right? So this becomes the sum of pk squared trace of this. What did I call that trace? Theta k, right? So I'm going to write this more simply as the sum of pk squared theta k squared, okay? So my problem, the problem I need to solve, okay, here, I'm reminding you of the definition of theta. So the problem I need to solve is, well, where is it? Minimize over A, left stochastic with these Perron entries, right? The sum of pk squared theta k squared, correct? Given the thetas, solve that problem. Okay. So this is how I'm going to solve the problem. I'm telling you what the answer is, and then I'm going to show you the answer, okay? The proof is not difficult. I will let you check most of it, but this is the answer, okay? The answer is this. I'm given the thetas, trace of H inverse GK. How do you find the thetas? In the next lecture, I'm going to give you algorithms to estimate the thetas, because technically you may know H, because you know the costs, for example. You may know H, or you may not know H. But you need this theta. This theta depends on the trace of H inverse G. It depends on the gradient noise covariance and on H. You may not know these quantities explicitly, so you need to estimate them. But let's assume for now that I know this theta, okay? If I know the theta, this is the A. You construct it as follows. You see, it has a very similar structure to Metropolis, except that you add these thetas as weights, okay? If you think of theta, what is theta? Think of it again. Theta is defined as the trace of H inverse G. This is like the inverse of signal to noise ratio almost, because G is noise. H, you can like RU is signal. This is like noise over signal, or one, right? Like one. So theta is like 1 over an SNR measure. That's an interpretation for theta. It's related to signal to noise ratio, okay? So what this is saying, this is the solution, and we call this matrix the Hastings matrix, okay? Because it appears in other contexts in papers by Hastings and others, okay? And these are the degrees, okay? And this particular matrix has these as Perron entries you can show. This is a theorem. It requires proof, right? This is one solution to the problem. Which problem? Okay, the problem I'm solving is this problem. Okay, I would like to minimize, so how, okay, I want to solve the problem of minimizing the sum of p squared theta squared over A, subject to the fact that A is left stochastic, P is its Perron entries, right? But the way I'm going to solve this problem, I'm going to forget the condition that A is left stochastic. I want to simplify the problem. I want to solve a simpler problem. I just want to solve this problem here. I want to solve, find those p's that minimize the thetas are given, subject to the condition that the p's add up to 1. Okay? And then I'm going to show you that the solution that you get, of course, they will be positive, and they will lead to an A that's left stochastic, and I'm going to find p's for you, right? The p's that I find, they will be positive, they will add up to 1, okay? And I'm going to construct an A such that this P is the eigenvector, the Perron eigenvector for that A, and that A is left stochastic. Then I would have found an A. All I want is to find an A, right? But rather than solve the original problem, which is difficult to solve, I'm going to solve a simpler problem and show you, by the way, this solution satisfies the condition. So this is just an indirect way of solving the problem. Okay? How do you solve a problem like this? For example, Lagrange multipliers, because this is just quadratic here, you see. Collect the p's into a vector, collect the theta squared into a diagonal matrix, right? Introduce the Lagrange multiplier. Just solve this problem. You get exactly that the p's, each pk, just p, is 1 over the corresponding theta, normalized by the sum of all the thetas. Each pk is 1 over theta, so it's an SNR, right? Like 1 over theta is like an SNR, normalized by the sum of all of the thetas. That's the solution that you get to this problem. Okay, this is what I showed here. Yes. I'm not including it. Okay, I'm saying I'm not. That's why. Okay. Okay, I'm going to use these conditions and show you that what I get satisfies the other conditions, and therefore I have a solution. I have one solution, right? That's how I'm solving the problem, okay? So that's why I did this here, okay? So, you see the P that I got here, these are positive P's, right? So they satisfy that condition. And then what I'm saying, construct this A. What is this A? On the off-diagonal elements, right, you put these ratios, and then you complete the diagonal elements so that they add up to 1. Okay? Very good. So now, I claim the only thing that remains to show is that this A is left stochastic, and that this A times the P's is P again. Correct? Okay. Checking that this is left stochastic is very easy. You just do the algebra. That the rows add up to 1 or the columns add up to 1 is not difficult, okay? Sorry? Left, the columns add up to 1, okay? So to show that A times P is P, again, this is just algebra, okay? I'll show it to you quickly. And then that completes the argument. To show it to you quickly, right, this is what I need to show. Right? Each column times the corresponding p's. So here it is, you see. I'm making k go from, right, 1 to n. So I want to show that this linear combination is p, correct? This is what I want to show, that A, P is P, correct? So you take a row here. Okay, so let's say the Lth row, you see here the Lth row, you change the column index. I want to show that that's P. Okay, if I show it, then I'm done. Fine? Because checking left stochastic is simple, I'm not doing it. If I show this, then I'm done. I prove the theorem. Okay? So this is how I show it. First, let me show you the symmetry relation, which is, okay, which is useful. So let's take ALK multiplied by PK, which is exactly what you have here, correct? Take these two scalars. I gave you the expression for A, I gave you the expression for P, correct? This theta cancels this theta. Well, I can replace it by theta L. Nothing changes, correct? Now this becomes AKL, because I switched, you see K became L. And this becomes PL, right? So this symmetry relation holds. If you switch, you see L to KK, if you switch K to LL, this relation holds. Fine? Simple to check. Because of this, now I can prove that it is left stochastic. How? Let's consider the sum now. Okay, consider this sum. What is that sum? So I remove the diagonal element AAL, PL, and kept the rest, correct? For the rest, I switched the indices. And then I put them together, right? Put them back together. I switched, I put them back together, this with that, correct? Well, but now this sum is over K, so this PL here can go out. And because it is left stochastic, you get PL, right? Okay, so the algebra is not difficult, but there it is, okay? So the interesting thing here is that I found an A that minimizes the MSD, right? This is 1/8. We refer to it as the Hastings rule, okay? Now this A will turn out to have some useful properties. So since this minimizes the MSD, of course, the MSD that you will get, if I take now those P's and plug back into the MSD expression, I will get the smallest possible MSD I can get for that network, correct? No, I'm getting there, right? You did not let me finish my statement, okay? If I take those P's and plug them into the MSD, I will get the optimal MSD I can achieve. Will it be better or worse than the doubly stochastic MSD? Because this is at least, right? Because this is the best you can do. Okay, so it will be better than the centralized, right? Okay, of course, this may look puzzling at this moment, right? How can it be better than the centralized? Okay. Yeah, exactly. So there is an issue which I'm going to explain later, but forget this point for now. It will definitely be better than the non-cooperative, but what about at the individual level? It will turn out that at the individual level it will also be better. Each one of them will individually be better, always. Okay, so let's prove it, right? Okay, so here it is. Okay. Or another aspect that I still need to show is that this A0 that I constructed is primitive. Okay, because if you remember, all the MSD expressions I derived in the previous lectures were under the assumption that the network is strongly connected, which means that A has to be primitive, which means one of the diagonal elements of A has to be positive. That's all. If you can show that at least one K is positive, actually all of them will be positive. I do the algebra here. I will not do it. Just write down what the algebra is. Okay, and it is here. Okay, so the way I'm doing it, just so that you see, this is the expression for ALK, right? This is definitely smaller than the numerator. I keep it unchanged. The denominator, this could be the maximum or the smaller value. So obviously this is always smaller than that, which is smaller than this. Okay, so this property holds. Okay, if this holds, then if you add all the A's, okay, on a particular row, except for the diagonal one, okay, so this will be upper bounded by that, right? You are adding, okay, 1 over nk how many times? Nk minus 1 times, because, right? So that sum is nk minus 1 over nk. But if I add akk to it, this sum should have been 1. So akk is 1 minus that, correct? So that's it, 1 minus that. You get something which is positive, right? So actually every diagonal element will be positive, so your matrix is primitive, right? Very good. So I don't have to worry about that. So now the interesting thing, if you take those pKs, optimal pKs that I derived for you, and plug them into the MSD expression, okay, right? Because remember, what was the MSD expression? It was proportional to the sum of theta k squared, pk squared, right? And now each one of these pKs is 1 over theta k squared, the sum of, correct? So you see that this cancels that. Okay, you're going to get something like that, okay? This is the optimal performance. Fine? Okay. The optimal distributed performance. Okay? In the doubly stochastic case, if you go back, you see, in the optimal case, you get the inverse of the average of the inverses of the thetas, right? It's like a harmonic mean, okay? Whereas, if you go back to the expression for a doubly stochastic solution, okay, this is what you get. Fine, just go back to the expression, put the p is equal 1 over n. This is what it is. So here, right, and there is a relation, by the way, that tells you how this relates to that. This inequality, you can prove it. This is an algebraic inequality, okay, a homework problem, okay? For any collection of n numbers, non-negative numbers here, the sum of a's times the sum of 1 over a's, this product is always larger than or equal to n squared. So I can compare this sum to the sum that appears in the previous expression, which involves this, and conclude that that MSD is smaller than this MSD. You understand? Okay? So there it is. So this best MSD, right, is better than the MSD you would get in the doubly stochastic case, right, which is intuitive because we optimized it, right? And obviously better than the non-cooperative solution. So far so good. But what about the individuals, right? The individuals. Well, here it is. What is the performance of each individual agent in the network? This is the expression. It is the same network MSD expression. Well, if I ignore the sum and keep only one of the elements, you see, 1 over theta squared is smaller than the sum. So the inverse is larger than the inverse of the sum. So obviously less than or equal. And this is exactly the performance of the non-cooperative solution, right? Because what is the inverse of 1 over theta? This is simply theta, correct? Which is the trace of H inverse GK, right? So you see, you do get that the Hastings rule ensures that not only the network is performing better than the centralized solution, better than the non-cooperative solution, but also better on an individual basis. You understand? Interesting, right? Okay. Of course, the question is, this is all very nice if I can find what the Hastings rule is. To find the Hastings rule, I need the thetas, right? I need to know trace of H inverse G, okay? And in general, I don't have, for example, in the mean square error case, I don't have the RU, which is the H. I don't have the G, which is sigma V squared RU, right, proportional to that. So knowledge of these quantities require that I know, right, requires that I know the noise power and the regression power, which I don't know. So I have to estimate them. We'll do that next time, okay? But if I could estimate them, I can design a network that will outperform the non-cooperative solution and the centralized solution. Now you might say, how can a distributed solution outperform a centralized solution? Okay, why? The reason why is because you are giving the distributed solution more information. The distributed solution is using the A's, correct, to do the combinations. And those A's are defined in terms of the SNRs. You are telling the distributed solution what the SNRs of the different agents are, essentially, right? And telling them to give more or less weight to information arriving from these agents in accordance to their SNR. The centralized solution is not using any of that information, right? It's just using the data. The new weight is the old weight minus a step size times the sum of all the gradient vectors, right? And these gradient vectors are not being weighted by any information that tells the algorithm give more weight to this gradient vector than this other gradient vector, right? The distributed solution is doing that. That's why it can perform better. You understand where this... So it's not puzzling because of that. Okay? Okay, so we established this. Okay? So this statement is stating what we proved. Okay? And this is just an example. Let's go back to an example. Same step size, uniform covariance. Okay? Here it is. So remember, the theta is the trace of H inverse G. If you do the calculation, this is the theta. Okay? now train the algorithm using the Hastings rule under this theta. By the way, sometimes, for example, the Hastings rule involves thetas up and down, correct? Remember that each A had something like this. The maximum of something like this, correct? Right? For example, if the noise variances happen to be the same across the ages, they will cancel out. You don't even need to worry about them. So sometimes, right, the theta cancels out. You don't really need to estimate it. Okay? In that case, if it cancels out, you end up having the metropolis rule, right? You get, so the metropolis rule ends up being an optimal solution, right, in this case. Okay? Okay, so here it is. I'm writing what the A is for this case using the thetas that I showed you. That's all. This is just an example specializing the result to the quadratic case, okay? Very good. You already saw that the distributed solution is better than the non-cooperative solution, and this is the performance, okay? And then you can do this for online learning where you have a single cost. So H is uniform across all agents, and the gradient noise, this is the real case, it's RS, it will be uniform across all agents. So theta will be uniform across all agents. It will cancel from the numerator and the denominator. And what would be the Hastings rule in this case? The metropolis rule. So the optimal rule for learning, for online learning in this case, is the metropolis rule, which happens to be doubly stochastic. So if you run this rule, okay, to solve a learning problem for any risk that you choose, this rule will be such that it will perform, okay, in this particular case, because it's doubly stochastic, it will match the performance of the centralized solution, like we showed earlier in this lecture, but it will perform also individually better than each individual agent, right? Because this is the Hastings rule in this case. Understood? Okay, very simple. Okay. Yes.
Is the Hastings rule the only?
No. There are other solutions to that problem, and in some of your homework problems, I asked you, okay, to check that. Okay. There are other. This is not the only solution. There are others. Okay, but this is a popular one, a famous one. Right? So now I already did the comparison with the centralized solution, that the optimal distributed solution performs better. Why? Because, right, this average here, okay, you see here you have 1 over n, the sum of the thetas, that's the usual average, okay? And here you have the inverse of the sum of the 1 over theta squares. This is related to a harmonic mean average, okay? And because of the relation between these two sums that I showed you before, the distributed solution will be better than the centralized for the reasons I explained, okay? The question now, can I modify the centralized solution in order to match the performance of the best distributed solution? And the answer is yes, give it this additional information. How, right? So this is what you can do, okay? This is the distributed solution we used before, correct? In this distributed solution, you are giving the same weight 1 over n to each gradient vector, right? If you modify it and weigh the gradient vectors in proportion to this p, remember this is the optimal p that was given as 1 over theta k squared normalized by the sum, right? So this p is proportional to the SNR. So you are giving more weight to better gradient vectors, right? So if you use that p here, right, and derive the MSD for this algorithm, the MSD for this algorithm will match the optimal MSD we derived for the network. Okay? You understand? Now, by the way, it's very easy to derive the MSD here without having to go through all the derivations we did before. Because you see, if I am to define the gradient noise here, okay? Come back here. The gradient noise is the difference between this gradient and the actual gradient, correct? There is 1 over n here, okay. the gradient noise here, I can define it as the difference between, you see, put 1 over n times n here, okay? np this hat minus np the true gradient, right? So the gradient noise here is proportional to the gradient noise in the previous case, and the proportionality is n times p, correct? You understand? I can write this as 1 over n times np times this. So the only difference between this and the other is that there is a scalar np multiplying the approximation that I'm using, okay? So the gradient noise here is a scalar times the previous gradient noise. So the covariance matrix here is np squared times the covariance before, correct? Okay? And the Hessian here, because the function is multiplied by np, right, is np times the Hessian before, correct? So all you have to do is go to the MSD expressions that you use for the centralized solution, replace the Hessian by np times what it used to be, replace the gradient noise covariance by np squared of what it used to be, and you get the results. You understand? I'm trying to solve it without having to redo all the calculations, right? So here, you see, it is as if I have scaled the costs by np, okay? This is the original gradient noise. This is the new gradient noise. Okay, so you see that the new Hessian matrix and the new gradient noise, okay, they are scaled accordingly. So just go to the expressions. If you carry out these scalings, okay, you will find out that the new MSD, right, because the new theta is np times the old theta, and the new p here, we know what it is, you will find out that the expression will match. You understand? So if you scale your weighted solution in a similar manner, you can recover the best distributed solution, right? So that was not an anomaly. It's just because you are not giving enough information to the centralized solution, correct? So you see, once you have these expressions, you can answer questions like this. You can now play with the network, right? Design your A, compare how different networks perform, right? Okay. And then I have a simulation here just to show you that this is indeed possible. Okay, so this is the step size. Okay, uniform H, this is G, this is theta. What I'm doing here, I'm running now 3 algorithms. Diffusion, using the optimal A's. So this will be the best network you can get in this case. The usual centralized solution, and the weighted centralized solution with the optimal weight. So what do you expect to see? The learning curves of this and diffusion to be almost on top of each other, and this to be worse, right? And the simulations confirm the theory, okay? So this is what you're going to see here. This is the network. This is the noise power, and RU is uniform across the agents. And if you plot the learning curves, this is what you see. Okay, you can see that the red curve is the regular centralized, the black curve here is diffusion, and the one a little bit below it is the centralized solution, okay? You see, and it matches the theoretical expression we derived, okay? So you can recover that performance if you normalize the entries of the centralized solution accordingly. You understand this point now? Convergence rate is the same, okay? So now you can repeat all of this for the excess risk, okay? So I'm going to rush through this part because you will be bored, okay? And I will be bored, so, okay? But I'm showing it to you here so that you know, just like we have results for the MSD, we have the same results for the excess risk. So let me go through this quickly. In this case, I'm assuming all the agents are interested in minimizing the same risk function, okay? These are the expressions, just like for the MSD we had before. Again, when you have doubly stochastic, this will match the centralized, okay? Will be better than the average, okay? But not necessarily better than the individual. Same issues, okay? Okay. Same issues, okay? Again, not necessarily better, and I give an example here of two agents with, okay, not necessarily better. So then I formulate the same problem. Let's find the A that minimizes the ER. The solution turns out again to be the Hastings rule. The only difference here between this and the MSD is that theta now is defined differently. Theta now is simply the trace of R, because this is the real case. There is no G, there is only RS, and H doesn't appear. You see, if you go to the ER expressions, you don't see H inverse. Right? That's the difference. H doesn't appear. So theta is different, that's all. Okay, but everything else, the mathematical formulation is the same. Okay? Here, you will get the same solution, Hastings rule, and then you will be able to show that the optimal is better than the distributed solution and better at the individual level. Okay? And then here I have an example to show that. Okay? Comparing distributed and centralized learners, uniform step size. Okay? I run diffusion. This is logistic diffusion, okay? So the agents are solving a logistic regression problem. And here I'm running a centralized, weighted centralized solution in this case, okay? In this case, the Hastings rule in the learning problem is the metropolis rule. So it's doubly stochastic. So the scaling will just involve, okay? Anyway, if you run these are the expressions we derived. Okay, let me just show you the simulation. This is the simulation. Okay, you can see that, of course, it's a little bit better, the centralized solution. Okay, these differences here are due to the approximations we do in the analysis. Okay, but if you use a smaller step size, because the theory says they are the same to first order mu, so mu has to be very small. So if you reduce mu further, of course, these curves will get closer and closer. Okay. But the point is that they both are going to the theoretical results we derived, right? So the excess risk part of this lecture is very similar to the MSD part. Fine? Okay? Very good. So today, okay, what I did today was to use the MSD or ER expressions from last time and try to design now the combination policy optimally. Let me pick the A that gives me the best MSD or the best ER, and I gave you one solution, the Hastings rule. And I showed you if you use that solution, the whole group will benefit as a group and also individually, right? And we established that analytically by comparing the expressions, okay? So in the next lecture, we are going to use these expressions a little bit more and get a little bit more insight into other aspects related to the behavior of the network. Okay, some surprising effects come up that you're going to see in the next lecture. Okay, so I'm going to take a break for 1 minute and then we move to the next lecture. Okay.